Welcome to Unit 8, Inference for Categorical Data, chi-squared. This is topic 8.6, carrying out a chi-squared test for homogeneity or independence. So in the previous videos, we've covered chi-squared goodness of fit, which is for one categorical variable. And then in the previous video to this, 8.5, we talked about setting up a chi-squared test for homogeneity or independence, which involves two categorical variables in a two-way table. We covered steps 1 and steps 2. In this video, we're going to cover steps 3 and 4. So step 3 is really actually quite simple. It's actually doing the math. It's a little time consuming, to be honest, but it's the step where you're going to do the math. We're going to calculate the chi-squared statistic for your data and find the p-value. Now, there is only one grand chi-squared statistic for all of your data. There's a bunch of what we call component chi-squareds for each individual category, but you add them all together to get your grand total, your one chi-squared statistic that represents all of your data. And then we're going to use chi-squared CDF on the calculator to get that p-value. And then step 4 is really making a nice conclusion in context about what that p-value tells us. All right, so step 3 is getting that chi-squared. So remember, this is the only formula for chi-squared. It's a very simple formula. We take the observed counts in each category minus the expected count for that category squared divided by the expected. Now, you do have to do this for every single category, and then this summation symbol right here tells you once you have all of your what we call component chi-squareds, you add them all together to get the grand total chi-squared. Then, once you have that grand total chi-squared, you could very easily get the p-value using chi-squared CDF on your calculator. Again, you access this command by hitting second variables or second vars on your calculator and scrolling down. This is the same place where we typically go for normal CDF and TCDF. Just scroll down a little bit further. The only new part is actually find the degrees of freedom. So the degrees of freedom when you're working with two categorical variables is a little bit different. Remember, if there's only one categorical variable, you just take your total categories minus 1. It has nothing to do with sample size. Well, here the degrees of freedom is row categories minus 1. So you look at how many different rows do you have? How many categories do you have for your, I'm sorry, I just lost my train of thought there. How many categories do you have going down the rows? Take those categories minus 1, and then your column categories minus 1, and you multiply those two numbers together. So it's a little bit, it's kind of weird to talk about. That's why I stumbled there for a second. But once you actually see a two-way table, it's actually really simple. Just be careful you don't include the totals. The row total and the column total do not count as categories. So you're actually talking about the individual categories of the categorical variable for each rows and columns, minus 1 each, and then multiply those together. So for a test of independence or homogeneity for a two-way table, the p-value is the proportion of values in a chi-squared distribution with appropriate degrees of freedom that are equal to or larger than your chi-squared test statistic. So remember, a chi-squared model is skewed to the right because you can only have positive values since there's a square involved in the formula. So your chi-squared number is going to fall somewhere on this model. Remember, it's just like a sampling distribution that has tons and tons of z-scores or t-scores. A chi-squared model has tons and tons of chi-squared values. So once you identify where yours is, for example, let's say our chi-squared falls right here. Then what happens is the p-value is looking above that. The p-value is the proportion of other chi-squareds that would be even higher than yours. Okay, and that's why we always go to the right. All right, so let's talk a little bit more about that p-value. So oftentimes you might have to interpret the p-value. I do want to make a very important note here, big star here, right? You don't have to interpret the p-value in a typical problem, right? You just have to find the p-value and make a conclusion based on it. But sometimes there might be a follow-up question that actually wants you to interpret what that p-value is. So a p-value for a chi-squared test for a homogeneity or independence is the probability, given that the null is true, of obtaining a test statistic as or more extreme than the one you found. So again, it's basically saying, hey, what's the probability you get a chi-squared number as equal to yours or higher than the one you found? And that is what the definition of a p-value is. All right, step 4. I mean, we have gone over this so many times by now. I really hope this is finally sunk in. But making a conclusion is all about comparing your p-value to the level of significance. Most problems will give you the level of significance. If not, you get a pick. Typically, the level of significance we choose is 1% or 5%. So if your p-value is below that level of significance, we will reject the null hypothesis and say that we do have significant evidence that the alternative hypothesis is true. A low p-value is basically saying that the probability of your chi-squared value being found or higher is extremely unlikely, but since it was found, that's what gives you evidence that the null is wrong and the alternative must be true. If the p-value is above the level of significance, we fail to reject the null hypothesis and say that we do not have significant evidence that the alternative hypothesis is true. So if your p-value is quite large, well then what that means is that your test statistic, which came from your sample, so basically they're saying your sample is very likely if the null is true. Well, if your sample is likely if the null is true, then that means that it's not weird and the null probably is true. So that's why we fail to reject it. So make sure you do word your conclusion properly based on it being a test for homogeneity or a test for independence. And what I mean by that is if it's a test for homogeneity, you're talking about, hey, is the distribution different across the population? So make sure that that's part of your answer. Yes, there is evidence that the distribution is different across the populations. If it's a test for independence, we're looking for, is there an association? So if you reject the null, you would be saying, yes, there is an association between variable this and variable that. All right. So make sure, the results of a chi-squared test for homogeneity or independence can serve as statistical reasoning to support the answer to a research question about the population that was sampled or populations that were sampled, independence or homogeneity. So the key idea here, the important part about this slide is basically saying that, what you determine at the end of a chi-squared test can be actually used as statistical evidence to support your conclusion. So if you're going to conclude that the alternative is true, well, a chi-squared test, this whole ending to a test is actually good, sound evidence to show that. All right, and that's actually true with any significance test that we've learned. All right, let's jump and look at some examples. So one example that we looked at last video that we started in the setting up section was, is there evidence of a difference in the proportion of favored social media across these different populations, or is it all the same? Yeah, the numbers might be a little bit different here, but essentially are they the same? So we're going to conduct this at the 1% level. We already went through our hypotheses. The null is that there is no difference, and the alternative is that there is a difference. So make sure you have that good context there. And we've seen this before. We saw this exact same stuff in the last topic video as well. The conditions are very simple, same conditions we've been working with. Samples got to be random to avoid bias. Sample has to be under 10% of the population. Each of the samples, remember there's actually 3 samples here, middle schoolers, high schoolers, college students, and that every expected count was 5 or more. So these are the expected values that you actually also have to find in step 2 here. So quick recap on how to do that. I'm not going to show it because we went through it in topic 8.4 and 8.5. But you basically, to find the high school kids that we expected to favor Instagram, you take the row total times the column total and divide it by the grand total. And that's why I came up with 129.82. Now, if these numbers all hold, it just goes to show that we have the same percentage across the board, not the same number. Why not the same number? Because our sample sizes are different. If all of our sample sizes were the same, 100 middle schoolers, 100 high schoolers, 100 college kids, yeah, then we would see the same numbers across the board. But they're not, and that's why we're seeing slightly different numbers, but they're all proportionally the same. All right, now we get to move into the good part, right? This is the part that I think is easy, but if you'll notice, it is very time consuming. So we have to find the chi-squared value. So for every single one of these categories, again, you don't use the totals, right? We're just looking at the observed counts for each population and each social media preference. So we do have 9 of them. So this is a little bit time consuming, but for each one of these, we take the observed, for example, 12 middle schoolers that use Facebook, minus the expected, 21.05, square that value and divide it by the expected. So this does take some time. And unfortunately, that is one of the bad things here, but it's not really difficult work. You just got to take your time to do it. Now, when you are using your calculator to do this, make sure you use parentheses. So I'm going to do 12 minus 21.05, end that parenthesis, make sure the square goes on the outside, and then divide by 21.05. So type it all in at once, but use the parentheses. Obviously, you could do it step by step, but make it easy on yourselves. And then you just got to repeat that process, unfortunately, 9 times because there are 9 different categories here. So again, that particular chi-squared component was 3.89. So I actually have the work shown here for all 9 of the values. And you will notice that, for example, this one right here, 0.00025, very, very small. That means that what was expected and what was observed were really, really close together. That's probably going to be this one right here. I mean, look, the observed was 130. The expected was 129.82. And then others were a little bit bigger, but not huge. I mean, this 5.57 was a little bit of bigger difference between them. And that was probably this one right here, 44 versus 30.88. But again, add them all together, and the grand total was 12.589. That's the grand total chi-squared value that you really, really need to get. So just take your time. It is time consuming. I cannot lie about that, but take your time to get all those values. Then comes the p-value. So remember, let's talk about the degrees of freedom real quick. So I'm actually going to go back to the chart. So we have 3 variables down this, 3 categories down the left-hand side for the rows. Middle school, high school, college. We have 3 categories across the top: Facebook, Instagram, Twitter. Do not count the totals as categories. So 3 minus 1 is 2. 3 minus 1 is 2. 2 times 2 is 4. So we have 4 degrees of freedom in this problem. All right, so the chi-squared value, remember, it's the probability that any other chi-squared is greater or equal to the chi-squared that you got, 12.589. So to find this probability, we're going to go to chi-squared CDF on the calculator, 12.589. Then we're going to go to 999, which is 99, really just 99 is fine. That's just acting as our infinity, and then 4 degrees of freedom. So let me briefly show you how to do this on the calculator. So second vars. Go all the way down to number 8, chi-squared CDF. You're going to type in 12.589. And I forgot the 89 there. And we're going to go, again, I like to go to 999. Really, 99 is fine, but you're going really, really, really high because of the fact that, you know, it's skewed to the right. There is no left. It's all to the right. So we're going to go way to the right. And then make sure you change the degrees of freedom there to 4 degrees of freedom. Paste that to your home screen. And we get a p-value of 0.0135, 0.0135. Now that's an interesting p-value because that could really kind of reject the null or not reject the null. So if you go back to the problem, I did ask you to conduct the test at the 1% level. So that is really going to actually make a difference in our answer here. So again, 0.0135 was our p-value. Okay, so now for the conclusion. I'm not going to lie, it's close, but you got to follow the letter of the law. So since my p-value of 0.0135 is greater than 0.01, I will fail to reject the null hypothesis. There is not enough statistically significant evidence to suggest a difference in the distribution of social media preference across the 3 populations of middle school students, high school students, and college students. What a great conclusion. There's a lot of context I have there. So remember, when we fail to reject the null, we're saying that, listen, yeah, this, you know, it was close here. Sorry, but it is what it is. We're basically saying, hey, we're failing to reject. There is not quite enough evidence to suggest that there really is a difference. Yeah, go back and look. Some numbers were a little bit off, but most of them were actually not that far off to say that we can clearly say that there is a difference in the distributions across, okay? So it appears that there is no major difference of social media preferences across the population. So make sure you give a nice, well-worded answer in context. Now, this is a great problem to see because, like I said, boy, was it close. Our p-value was so close to the significance level. So understand there really is a difference in the distribution of social media preferences, but we just didn't see enough to convince us of that. So we could be making a type 2 error, but that is just the nature of all inference problems. I mean, you know, I don't know. At the end of the day, I don't know. I only have the numbers in front of me. So is there a difference in social media preference or not? I mean, I don't know. The test does give me reason to reject the null. The test is saying that there's just not enough evidence for me to say there really is a difference. But listen, at the end of the day, maybe there really, really is a difference across these populations in terms of social media preference. So maybe I made a type 2 error, right? The type 2 error is when the alternative is true, but we fail to see that. But listen, I don't know if that happened or not. It sucks that the p-value was so close to my level of significance, but you've got to make the decision based on how we teach you. So 0.0135, as close as it is greater than 0.01, so I have to fail to reject the null. So this is just the nature of all inference problems. That's why we love really, really small p-values, because then we're super confident we made the right decision. Or we like really, really big p-values because then we're pretty confident that, hey, there isn't enough evidence to go with the alternative. Here it's close, but we have to make the decision we make. So it's a good problem to actually have this happen, to understand that this does happen with significance testing. All right, let's look at our next and last example about political parties. So remember, this was one sample of voters from a large county in California, and we asked them their gender and we asked them their political party affiliation, Republican, Democrat, Independent. So the question says, does this evidence show that there is an association between gender and political party affiliation? And it wants us to use a 5% significance level. Okay, 5% significance level. All right, so the hypotheses that we discussed last video in 8.5 is that there is no association between gender and political party. So notice the context there. So not only am I saying that the answer is, sorry about that, move things around a little bit there. So not only am I saying no, that there is no association, I'm also bringing up no association between what? You know, some kids will just say there is no association. You're not going to get full credit for that. You got to give the context between gender and political party for voters in this county of California. And the alternative, again, sorry, there's a little typo there. Should be a little H sub A there. Sorry, there is an association. The alternative is no, there is an association. Something about being a male makes me more likely to do this or less likely to do that. Okay, so now let's jump into step 2. Check those conditions. Should be pretty easy. And find the expected values. Once again, for example, how did I get 33.87 as the expected values for females that are independent? I took the row total times the column total divided by the grand total. And that's how I got 33.87. Okay, so just as an example of where these numbers are coming from, you know, 60% of people, 372 out of 620, 60% of people are Democrat. If there is no association of the females, 60% should be Democrat. Of the males, 60% should be Democrat. So these numbers aren't the exact same numbers, but they are the proportionally equivalent, if that makes sense. So that's another key thing here. A lot of kids sometimes make a mistake on chi-square tests and they use proportions. They want to use the proportion that was expected, the proportion that we observed. No, chi-squareds are all about counts. So even though I'm bringing up the 60%, I had to actually get the 60% value. You know, what is 60% of 340? That's the 204. What is 60% of 280? That's 168. So make sure you're always using counts, not proportions in a chi-square test. All right, so now comes the fun part, which is doing the work. And for every one of the 6 categories, male Republicans, male Democrats, male Independent, female Democrats, female Republicans, female Independents, so 6 categories, I have to go ahead and find that component chi-squared, add all of them together. So once again, let's just do female Republicans. So 20 was the observed, minus 78.3 was the expected squared divided by the 78.3. So there's that value right there, which ended up being 43.25. And I'm like, oh my gosh, that's a huge component chi-squared. That's an enormous chi-squared. If you look at the other ones, 26.8 is pretty big. This is actually pretty small. And the 3.84 is pretty small, but these other ones are all really, really big. So this is kind of, you know, I don't want to jump to conclusions, but these are huge values. That the bigger your chi-squared is, the more off you are from what you expected, right? So these huge numbers are telling me that I'm way far off from what was expected, which is a sign I'm probably going to reject the null. But we do need that p-value. So once again, the degrees of freedom, let's show that real quick. So 2 categories, male, female on the left, 3 categories across the top, Republican, Democrat, Independent. 2 minus 1 is 1, 3 minus 1 is 2, 1 times 2 is 2 degrees of freedom. So my p-value is the probability that any other chi-squared comes back more than mine. So if you think about that chi-squared model, 136.25 is probably way over here somewhere. So the probability that we are even higher than that is going to be very unlikely. So I use chi-squared CDF on my calculator, 136.25 to 999 acting as my infinity, 2 degrees of freedom, and you get an unbelievable value. I wrote a ton of zeros there, right? I think I counted them all correctly. You could actually check if you want. But that is unbelievable. This is basically saying, in a nutshell, that the data that we observed, the data that we actually observed in our two-way table is extremely unlikely to occur if there is no association. So guess what? this crazy scenario did occur. This has actually happened. So what's something that seemed impossible did occur. That's what tells me that, guess what? There is an association. So I'm going to go ahead and say that since my p-value is well less than 0.05, I will reject the null hypothesis. There is plenty of statistical significant evidence that there is an association between gender and political party affiliation for registered voters in the county of California. Notice how specific I am in being in this context and this conclusion. Please make sure you do that on the test. In this county of California, if you are a female, you are way more likely to be Democrat. And if you are a male, you're way more likely to be Republican. That's where I got these numbers from. You know, for example, if we look at the female Democrats, right? That was a huge component chi-squared, really, really, really big there. That was the 196 right here. I mean, that's just huge. It's a big number. That's the 196 minus 168. So that's why we're so far off. So it does seem that females are more likely to be Democratic and males are more likely to be Republican. So you don't have to necessarily give that last sentence there that I gave, but I'm just trying to show that, wow, there are some big differences in this table, which is alluding me to say that there is an association. So this is an example that's great to see because it's so convincing, right? We're not worried at all that we made an error here because the p-value is so low. We're very confident that we didn't make any kind of type 1 or type 2 error and that we do make the right decision in rejecting the null. All right, guys, that's it. Hopefully this video made a lot of sense. It really is a fairly simple process. It's not overly difficult. It's just a lot of little things along the way to get you to the end. But individually, they're all not bad. Maybe time consuming. I'll agree with you there. But overall, it's not too bad. All right, hopefully it all made sense and be ready for some practice problems.